Hi everyone. I hope this video is clear, right? Audio, video, everything is fine. In YouTube, in the comment section, please write your comments and try to make this is what you please try to interact with me as much as possible. Okay. So, like in the last class, I have taken a couple of slides to give some intro about digital, like what it is and all. But in today's session, so directly you will be starting with taking the questions. Okay. So everything is fine. Audio, video, everything is fine. Okay. Video is blur. Video is blur. I think issue might be at your end, Sivan. It seems to me it is appearing fine only. Please, make your resolution to 720. Those who are facing issues, make it to 720. I think it will be all right. Okay. So, like the last class, this time also I have taken a couple of questions. Okay. So, here is the first question. X is equals to x1, x0 and y is equals to y1, y0 are 2-bit binary numbers. The Boolean function s that satisfies the condition x greater than y, then s equals to 1 in its minimized form is. So these are the 4 options I have given. So this question is basically from combinational circuit topic and from the comparator concept. If you see this closely, right? So there are 2 numbers, and I mean x and y. So both of them are of 2 bits. So if x is greater than y, then s should be 1. Then which of the following is indicating the expression of s in its minimized form? Nikhil responded something. Okay, fine. So let's see how do you answer this. All of you, please. What is the answer you are getting? So basically, what I can tell is we have 2 numbers, namely x. It's a 2-bit numbers, x1 and x0. And we have y, which is again a 2-bit numbers, which is y1 and y0. And we need the conditions such that where x is greater than y. This is what we need, right? So x can be greater than y. So what are the conditions? That is, one condition is your x1 is 1, y1 is 0. Okay, this is one condition. Or, okay, or what may happen is if you are able to, get x1 is 1, y1 is 0 from here itself, we can say. If this is not happening, then the other condition possible is x1 equals to y1. Okay, I mean x1 and y1 are same, that is both can be 0, both can be 1. And x0 equals to 1 and y0 equals to 0, right? So if you see this, so this is the expression of s, and s is equals to x1 y1 bar plus. So how much this will be? This will be x1 x0 with y1 and with this is x0 y0 bar, right? And why I'm using x0? Because the property of x0 is when x and y both are same, you get the x0 combination is basically 1, right? So you have to simplify this and you have to cross check. So accordingly, you'll get the answers. Nikhil and Mona Lisa, you said the answer is B. So let's see. So this is x1 y1 complements. This is x1 y1 plus x1 bar y1 bar. This is ANDed with x0 y0 bar. So this is x1 y1 bar plus x1 x0 y1 y0 bar. Then with this, if you do plus x1 bar x0 y1 bar y0. So total how many terms you got? So you got 3 terms, right? So now you have to check which of the following is correct. So if I see, so option B having the first term x1 y1 bar, if you see this, so this is the term we have. So it seems B will be the answers. So basically, if somehow, if I'm able to do, the minimization of this, if I'm able to get that expressions, I can easily tell this will be the answer. So This is, you can see, this is x1, y1 bar. And what is common among them? So I think, what is common among them? So y1, or you can also make use of K-map also, no issues. Right. How do you verify this? Either you use the K-map or even you can try the mean term combination. So that will also work. So x1, y1 bar, that is fine. So how much the mean terms you'll get from this? So from the, I just have to prove whether this B and this expression is equivalent or not. So x0 you can take common, it seems. So if you take x0 as common, so what is left? So what is left means this is x1, y1, y0 bar plus this is x1 bar, y1 bar, and this is y0, right? Otherwise, you can, if you try with this, so if you take a function x1, x0, y1, y0, okay, so you can check what are the mean term you're getting from this. So from this, your x1 is missing. So you'll have a vacancy here, right? So this is your x1, it's blank, then x0, then your y1, then your y0 bar, right? Y0 bar and y1 bar, okay? So this is 1, 0, 0, 0, 1, 1, 0, 0. So the mean term we are getting is 4 and 12. So this is, we are getting 4 and 12, right? And how much will you be getting from this? From this, if I see x1 is missing, then you have x0, then we have y0 bar, and then we have x1, right? So we can think of this is 0, 1, this is 1, 0, 1, again 1, 0, 1. So this is 5 and this is 13, 5 and 13, right? 5 and 13, 4, 12, 5, 13. So just verify this and you can get the answers accordingly from there. Otherwise, what somebody can do is you can also take the K-map, and from the K-map also you can see this will be coming same or not, right? I hope you can do it. I think Nikhil and Mona Lisa who have given the answer as B. I think by observing the term x1, y1 bar, I think you said the answer is B, right? I think so. So, okay, this is fine. So let me do one thing. Okay, unless until it is not complete, will not be satisfied, right? Okay, so this is x1, x0. This side is your y1, y0. So it's a 4 variable map. This is your x1 bar, x0 bar. This is your x1 bar, x0. This is x1, x0. This is x1, x0 bar. This is y1 bar, y0 bar, y1 bar, y0, y1, y0. This is y1, y0 bar. If I ask you to plot this, so where this will be coming, x1 and y1 bar. x1 means these two rows are selected, right? And y1 bar means these two columns are selected. That means if I ask you to plot it, so you'll get like this. Okay. Yeah, Mona Lisa, okay. So that way also, okay, Boolean algebra also you can do, no issues. By K-map if I'm solving, right? So you can see here, so x1 and y1 bar. So from these two row and from these two column, if I simplify this, I'll be getting these things, okay? Similarly, you have x1, x0, and then you have y1, y0 bar. x1, x0 is this row, and y1, y0 bar is this. This is what the cell is. Similarly, x1 bar, x0, that means this row, and then you have y1 bar, y0. So this is what the element is. So if you simplify this, okay, so this is anyway quad, okay, this is a pair, and this is a pair. So for this, if I ask you what is the expression you will get, so from the row, you'll get x0, and from column, you'll get y1 bar, y0. Similarly, for this, if I ask you, so from row, you'll get x1, x0, and from column, if you see, you'll get it is y0 bar. And of course, this is anyway, we know this is x1 and y1 bar. So answer is x1, y1 bar, plus this is what, x0, y0 bar, X0, Y0 bar, and Y1 bar. And then we have X0, Y0 bar, X1, X0, Y0 bar, X1. So this term, if you see X0, Y0 bar, X1, this is the term X0, Y0 bar, X1. And the middle term is X0, Y1 bar, Y0 bar. Is it Y0 bar? So this term is matching, fine. And Monalisa, you have taken it is by taking X1 and Y1 come. Okay, A plus A bar B equals to A plus B. Okay, that is also fine. So this is simplifications. You can check it. So this is fine. This is what basically this is Y1 bar. Okay. Y0 bar only. Okay. So please, check this. I think somewhere something is missed, but this is how it is actually. The problem is, so we got the first term we got. I mean, this one we got, and we got X0, Y0 bar, X1. This we also got. The middle term is basically this is X0, Y bar, but this is what is Y0 bar actually. So I think there is any issue with this one. I mean, the thing I have written, is there an issue with this? Why there is a mismatch is coming? Anyone? What is the expression we have taken actually? That was, if you remember, it was X1, X0 with Y1, and it was X1 and X0 and Y0 bar. This is what we have taken. So this was XY plus X bar, Y bar, and this is X0 and Y0 bar. If you simplify this, we said it is X1, X0, Y1, Y0 bar plus X1 bar, X0, Y1 bar, and Y0 bar. This is what we have taken, right? So here X1, X0, Y1, Y0 bar. This is X1 bar, X0, Y0 bar, and this is Y0 bar actually, you see. This one you see. This is coming Y0 bar, right? Yes, this is actually Y0 bar. Isn't it? So this, if I ask you to plot X1 bar, X0, X1 bar, X0 is this row, right? And then you have Y1 bar, Y0 bar. So this is what it will be, not this one, not this one, okay? So this pair will not come into picture. So this pair will come into pictures. If this pair is coming into pictures, then from row you will get X0, and from column you will get Y1 bar and Y0 bar. You see now this is coming. So this is what I missed, these complements, right? That's why it is, the problem is. So now you can see, so we got X1, Y1 bar from this quad, and from this group, we got it is X0, Y0 bar, Y1 bar, and from this one, we got it is X1, X0, and Y0 bar. So yes, this is matching option B. So sometime it happens. It's a simple problem. Okay, this is the solution. Yeah, let's go into the next question. Okay, this question you see. So initially I have taken some questions which are of kind of direct questions, and then we'll go into the challenging questions. The figure below shows ith full adder block of binary adder circuits. Ci is the input carry and C of I plus 1 is the output carry of the circuit. Assume that each logic gate has a delay of 2 nanoseconds with no additional time delay due to interconnecting wires. If the inputs AI, BI are available and stable throughout the carry propagations, the maximum time taken for an input Ci to produce steady state output C of I plus 1 is dash nanosecond. Okay, so this question is kind of based on delay concept. Yes. What is the answer? What is the answer? Now it is fine. Tell me. If the input AI be available and stable throughout the carry propagation, maximum time taken for our input Ci to produce steady state output Ci plus 1 is dash nanosecond. Nikhil is saying 60. 60 is no way it is correct. 60 is no way it is correct. Okay. So this is what is the key point. Input AI and BI are available and stable throughout the carry propagation. Basically, if you see this carefully, so this is a three-stage circuit as we know. So this is what your stage 1 is, or level 1 you can say. So this is basically level 2. And this is basically level 3. And as far as this question is concerned, our focus is on carry. Our focus is not on the sum. Our focus is on carry only. So if the delay of each gates are 2 nanosecond, 2 nanosecond, 2 nanosecond. So generally what we have seen is in theory, so we'll get this output at 2 nanosecond. We'll get this on 2 at 2 nanosecond, we get this output. So we'll get this output at 4 nanosecond. Why? Because at 2 nanosecond, this input will come and its own delay is 2. So 2 plus 2 will get this at 4. So at 4, this gate will receive the input. So 4 plus 2. So we'll get this output at 6 nanosecond. So generally we say the answer is 6 nanosecond, right? Okay, but whether the answer is 6, of course, 6 is the wrong answer. 6 is not the answer. So what's going to happen is, in this case, this delay we should not consider, or this delay should be ignored. Why this delay should be ignored? Because of this particular statement which I am highlighting repeatedly. The input AI be available stable throughout the carry propagation. That means you have to assume, like, when this CI is coming, so by that time this AI and BI long back they are available and they are stable. So basically it's actually a ripple carry adder where there are multiple stages. Okay, and in multiple stages, which is actually the thing which is coming, this is coming is the carry only. Let's say, for example, if you remember, so if I go for a 3-bit case, okay, which is like this, we have this AB input, right? So only thing is the carry used to propagate, the carry used to propagate. So I'm saying this and this are already available, and some value of time this particular CI is coming. So this CI is basically, you can think of this CI. So that way, that means this AI and BI are already available before this CI is coming into picture, right? So definitely, if before the CI comes, this AI BI are already available and stable. That means this particular output you see here carefully, and this particular output. So basically the output of this XOR gate and output of this AND gate. So they are already available. So the delay of the first stage will not come into picture here. Why? Because whatever the actual input to be this XOR gate and gates, okay, one of the input, that means this and this are already available to me when this CI is coming. So there is no lapse of delay of these 2 nanoseconds. So you can, for this particular stage, the reference you can think of, how much? The reference you can think of 0 only. Because for the first stage we used to consider 0, but for this we'll consider the reference is 0. Why 0? Because this stage is already available to me. So here I'll be saying this is already available. So at 2 nanosecond, I'll be getting this output. So this particular final OR gate, one of the input it is receiving from this AND gate. So at 2 nanosecond, it is producing the, it is receiving the inputs, and its own delay is 2. So 2 plus T, 4 nanosecond is the right answer. So 2 plus 2, 4 nanosecond is the right answer. Is it clear to all of you, please? The only thing is, in this case, somebody should understand is that the delay of the first level will not be considered in this case, because if the question would have been what is the maximum possible delay, then the answer would have been 6. But in this case, because this AI BI are already available, so there won't be any lapse of delay in the level 1. Okay, so level 1 will be definitely the same. 0 itself, you can think of the reference. Okay, so the answer is 4. The answer is not 6, answer is 4. I hope this is clear. Is it clear? This question is again a simple question, will come after some time. So let us answer this question now, which is a good question. Yes, please, in chat box, respond me. But the previous question is clear, the answer is 4. Okay. Now see this question. The circuit below shows an up-down counter working with a decoder and a flip-flop. Preset and clear input are asynchronous active low inputs. Assuming that the initial value of counter Q2, Q1, Q0 as 0, the counter outputs in decimal for 12 clock cycles are. Okay. So the circuit looks quite complicated, where you have decoder, you have up-down counters, you have a D flip-flop having preset and clear as active low inputs. And for this particular D flip-flop, the output of D flip-flop are connected to this counter to the count down pin and count up pin, right? This is what the thing is. So that means when this Q will be 1, okay, so counter will work in down mode. Okay, when this QR is 1, counter will work in the up mode, right? So this and this, these are the active high pin, you can see here. So when this pin will be 1, it will work in down mode, and when this pin will be 1, this will work in up mode. And of course, it will never happen like both of them are 1, 1, because Q and Q bar are complement to each other. If one is 1, other one will be 0, and vice versa, right? And again, it's a decoder, but what kind of decoder? This is definitely active low decoder, right? How do you know this? From the symbol itself, we know this is active low decoder. Okay. So what is being asked? The question is, okay, assuming the initial value of counter Q2, Q1, Q0 as 0, the counter output in decimal for 12 clock cycles. So this is the clock. So if this clock is triggered continuously for 12 cycles, what is the decimal equivalent of this Q2, Q1 and Q0? This is what the question is. So how do you answer? So the initial value is given 0, 0 and 0. So this is 0, this is 0 and this is 0. So this is given, right? So this is also 0 and this is 1. If this is 0, so this is 1, right? This is 1. So by default, all our initial condition we assume this is the situations. So now you can see, so now counter will work in the up mode. Why? Because initially we have taken this is 0 and this is 1. So this is 1 means this up pin is activated, down pin is deactivated, counter will work in the up mode. So far we haven't applied any clock. Okay, so far we haven't applied any clock. Now what is the tendency of a active low decoders? So the tendency of active low decoder is, for example, if I'm giving the input 1, 1, 0, which happens to be 6. So here Y6 will be activated. When I say Y6 will be activated, that means only Y6 will be output 0, rest of the bits will be 1. So if you remember, this is the tendency of a active low decoder. If it would have been active high decoder, if it would have been 1, 1, 0, if I give the input to the recorders, only Y6 will be high, remaining all will be low. But because it's a active low decoder, if you are giving 1, 1, 0, Y6 will be low and rest of the bits will be high. So this is what we know, right? So now taking this into considerations, let's see how we make the analysis. So I'm making here clock number 1, clock number 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. For 12 cycle we need. So initially clock number is 0. Okay. So we haven't given any clock and the initial condition is given is 0. So now you give the first clock. When you give the first clock, counter is in up directions. So counter will walk in up direction. So if the present state is 0, so the next up state is basically 1. So the next up state is basically 1 only. Yes or no? Next up state is basically 1. But if this is 1, that means this is 0, 0, and 1, right? 0, 0, and 1. That means here in this case, Y1 bar will be 0 and rest of the bits will be high only, right? But now you need to understand one thing. To this particular preset, what is connected? To this particular preset, this is Y5 bar is connected. And to this particular clear, what is connected? Y0 bar is connected, right? Y0 bar is connected. Okay. So now you have to see carefully regarding this Y5 bar and Y0 bar, because these are two pins are connected to preset and clear. So depending on what output we get, so it may happen like what the flip-flop may be resetted or it might be presetted. So accordingly, the counter may work in up and down directions. We should be careful about it. So first clock is gone. So we got the output 1. Then next clock will come again countering up directions. So next up state of 1 is 2. Again at 3, third clock is gone. So you'll get 3. Fourth clock is gone, you'll get 4. Fifth clock is gone, we'll get 5. So till this, it is the up count. It is working in the up directions. Now, when we give the fifth clock, so when you give the fifth clock, what's going to happen? When you give the fifth clock, so now this is basically 1, 0, and 1. So as a consequence, what's going to happen? Then this particular Wi-Fi bar, so this will be 0, rest of the bits will be high. So when the fifth clock is given, so the counter output is 101, and when 101 is processed by the decoder, it is making Wi-Fi bar is 0. And when Wi-Fi bar is 0, so now you see this preset pin is becoming 0. And when the preset pin is 0, what is the tendency of this? It will make sure the flip-flop initial condition is 1 and this is now 0. So now on the fifth clock cycle, you got 101 output of this counter. When 101 is processed by decoder, we got Wi-Fi bar is 0. And when 0 is given, it is making preset to 1. What is the consequence of this? Now the counter which was in up directions, now the counter will start working in the down directions. So up to fifth clock, it was working in up direction. So this all sequence we got based on the up sequence. Now what's going to happen? Now the counter will work in the down directions. So if the present state is 5 and the next clock is given, instead of going to the state 6, now this will go back to state 4. In the 7 clock cycle, again counter is in down mode only. So the down state of 4 is 3, down state of 3 is 2, down state of 2 is 1, and down state of 1 is 0. Now the moment when the 10th clock is given, so the counter will produce the output 0, 0, 0. Now when the counter is producing output 0, 0, 0, what's going to happen now? Now this Y0 bar will be 0, rest of the bits will be 1. So when this will be 0, so what's going to happen? Again, this counter, this particular flip-flop will be cleared. When this particular flip-flop will be clear, it means what's going to happen when I say this particular flip-flop will be clear. So what's going to happen? So this will be 0 and this will be 1, right? So again, the counter will start working in the up directions. So initially it was up. Now again, it is in down. But after 10th clock cycle, again, this will start working in the up mode. So the next up state of 0 is 1 and the next up state of 1 is 2. So this is what is the sequence is. So if the 12 clock cycles are given continuously, so you can see, so you'll get 0, 1, 2, 3, 4, 5, and then you have 4, 3, 2, 1, 0, and 1, 2. Right? This is what you will get. So what is the answer? So if you see this, answer is, of course, it is option D only. Answer is option D only. Okay. I hope this is clear, right? Fine. Now let us see the next questions. Let us take this one. In this question, you see this. For the 3-bit binary counter shown in the figure, the output increments at positive transition in the clock. Assume ideal diodes and the starting state of counter as 0, 0, 0. If output high is 1 volts and output low is 0 volts, the current I in milliampere flowing through the 50 ohm resistor during 5th clock cycle is. Okay, so let us try to answer this problem. So we have a 3-bit counter. Okay, the output increments at every positive transition of the clock. So it's a positive edge trigger, counter, right? Assume ideal diodes. These diodes are ideal. Starting state of counter is 0, 0, 0. So initial state of counter is 0, 0, 0. Output high is 1 volts. Output low is 0 volts. So current I in milliampere flowing through the 50 ohm resistor during 5th clock cycle is. So first thing is, so if the that means at 0th clock, so the state is 0, 0, 0. And it is given that it's a up counter because it increments at every positive transition of the clock. It's the up counter, right? So, and the question is about the 5th clock. So we are supposed to find something in the 5th clock. So in 0th clock cycle, the state is 0, 0, 0. Okay. So in the 1st clock cycle, the state will be 0, 0, 1. And so on and so forth. If I ask you what is the state of the counter in 5th clock cycle, the answer is 1, 0, 1. So this is the state of the counter on the 5th clock cycle. So this is your 1, this is your 0, and this is your 1. This is what is the information we can extract. So basically, now what I can do is I can remove this particular counters and I can redraw the circuit something like this. So I can think of I have a diode like this, and then I have a 100 ohm resistor here. Then again I have a diode, but in this directions as per the questions, and I have a 50 ohm resistor. And again I have a diode, which is of this directions, and again I have a 100 ohm resistor. But how much is connected to this? How much is connected to this? How much is connected to this? So because we are saying this is 1, and in the question is given output high is 1 volts and output low is 0 volts, right? So wherever logic 1 I'm getting, I'm thinking of this is 1 volts. Whenever I'm getting 0, I'm thinking of 0 volts. And whenever this is again, it is your 1 volts. Right? So this is 1 volt, this is 0 volt, this is 1 volts. Now, what I'm supposed to find in this question, I'm supposed to find this current I. That means current of 50 ohm resistor in this direction. This is what I'm supposed to find. So you tell me now, what is the state of these diodes? I have 3 diodes. Let's name this is D1, this is D2, and this is D3. So what is the situation of these diodes? What's going to happen? Now anything will be which will be forward bias, which will be reverse bias, or all will be forward, all will be reverse? What will be happening? So 1 volt is connected to this diode, right? So you can see here the P side is connected to positive voltage. So this is forward bias. 0 volt is connected to this diode. So this is, of course, again forward bias. N is connected to 0. And again, this will also be in forward bias. So I'm assuming like you all people have this much of basics from analog circuit you have learned. So I'm not going into this. So now in this case, these 3 diodes will be in the on state or the forward bias. So what is the consequence of this? So once the diode is forward bias, okay, the diode will be replaced by short circuit because ideal case. Okay. And again, the next diode is also replaced by short circuits. And again, the next diode is also replaced by short circuits. This is 100, this is 100, and this is 50. And here it is connected 1 volts. So I can think of a 1 volt source like this. This is 1 volts. And here also it is 1 volt, right? So I can think of this is minus, this is plus, and this is 1 volt. And this is 0 volt means I can think of this is my ground points. Okay. So this is what I can think of. Okay. So now I need to find this current I, right? I need to find this current I. So how do you find it? You may think of nodal analysis. So let's say this is your voltage Vx. So if you write the nodal analysis, how much you will get? Vx minus 100, sorry, Vx minus 1 by 100. Okay. I mean this path, if I ask you, Vx minus 1 by 100 plus Vx by 50 in the middle path. And again, in the last path, you'll get Vx minus 1 divided by, again, 100 equals to 0. Multiply 100 both sides. So you'll get Vx minus 1 plus 2 Vx plus Vx minus 1 equals to 0. So 4 Vx is equals to 2. So that means Vx is equals to 0.5 volts. But what is I? If you see the diagram, if this is Vx, so I is equals to, this is the I direction, right? This is what I need. So this is basically Vx by 50. So this is 0.5 volts divided by 50 ohms. If you simplify this, the answer is coming 10 milliamperes. The answer is 10 milliamperes. So this answer is 10 milliamperes. So it was not a very, tough question, but yes, little bit logical. Like you should have understanding of basics of diodes and counter to answer this. So first thing is, in the question, it is given that it's up counters, and we are supposed to find the current I in the 5th clock cycle, right? So in the 5th clock cycle, so the state of the counter is 101. That means here we are connecting 1 volts, here we are connecting 0 volts, here we are connecting 1 volts. So now this become, like once we are identifying all the diodes are forward bias, it is confirmed like this is now looking like a simple networks, and I have drawn this. And 1 volt is connected to this means this side is plus and this side is minus. 1 volt is connected to this node. It means this side is plus and this side is minus. So then by writing a simple nodal equation, I got the voltage Vx, and Vx by 50 is the answer, which is coming to be 10 milliamperes. Okay, I hope this is clear, right? We'll come to these questions after some time, but let us try to answer this question. This is one of the good questions. Okay, see this question carefully. The comparator's output equals to 1 when input is greater than equal to 0 and output equal to 0 when input is less than 0. Exclusive OR gate and the unity gain low pass filter given the circuits are ideal. The logic output of the exclusive OR gates are 0 volts and 5 volts. The cutoff frequency of low pass filter is 0.1 Hz. For V1 equals to 1 sin 3000 t plus 36 degree and V2 equals to 1 sin 3000 t volts. The value of V0 is dash volts. Okay, so I need a bit more space. 1 second. Yeah. Tell me, how do you answer this problem? So what informations are given if you see this? So V1 is a sinusoidal quantity and even V2 is also sinusoidal quantity. Okay. And this is a low pass filter whose cutoff frequency, okay, is given 0.1 Hz. And we are supposed to find this voltage V0. So what do you think? This question is from which subject? This question is from what? Analog, digital, signal, or what subject this question is? So because we are using comparators, you can think of analog, and because we are using XOR gate, you can think of digital, and because we are using low pass filter, you can think of signals, right? So such kind of questions by linking multiple subjects these days, we are getting frequently. So let us try to answer this question. Okay. So how do you answer this problem? What is the property of a comparator? I believe all of you know the property of a comparator is it compares two voltage. Okay. And in the question itself, the description is given like if the plus terminal voltage is greater than minus terminal voltage. Okay. So we get output logic 1, and otherwise you get it is 0. So let's do one thing. Let us try to, so let's name this is V3. Let's name this is V4. Let's name this is V5. And this is anyway V0 is given in the question itself. Okay. So now how to find this V4? Let's start with V4, the simple one. So V4, if I ask you, so V2 will be compared with 0. So one thing I can tell, if V2 is greater than 0, okay, then your V4 is equals to logic 1. And if V2 is less than 0, if V2 is less than 0, so we'll get V4 equals to 0. Okay, because the inverting terminal is given 0, non-inverting terminal is given V2. So when the V2 is greater than 0, that means when V plus is greater than V minus, you get V4 is 1, otherwise you get this is 0, right? So based on this, let us try to plot this. So if I'm plotting, so this is, let's call this is omega t axis. And this, if I say B2 means this is the waveform I'm interested to plot. Let's take up to 2 cycles. So this point is your 0, this point is your pi, this point is your 2 pi, this point is your 3 pi. So this is what? Nothing but your what? V2. Okay. And if I ask you to plot V4, so how much you'll get? So you can see between 0 to pi, so V2 is positive. So you'll get it is logic 1. So this is pi, this is 2 pi, this is 3 pi, and this is 4 pi. So pi, 2 pi, 3 pi, and this is 4 pi. So between 0 to pi, you can see V2 is positive. So you'll get logic 1. Between pi to 2 pi, okay, between pi to pi, this is less than 0. So V4 will be 0. Again, between 2 pi to 3 pi, so this will be logic 1. Again, between 3 pi to 4 pi, it will be 0. And so on and so forth. So this is the waveform of V4. But I need what? I need V5. To get V5, I also should derive what is V3 is. Okay. So how do you get V3? To get V3, again, we have to draw V1. And by comparing V1 with 0, you should be able to conclude how the waveform of V3 will look like, right? So now the question is how this V1 will be, okay? So V1 will be, how it will be means, again, I'm taking it, say, omega t axis. So if you see basically, so this 36 degree can be written as pi by 5. 180 by 5 is 36 degree, right? 180 by 5 is 36 degree. So basically with respect to V2, so V1 is phase shifted, or basically this is kind of advanced version of V2. In other words, if I shift V2 pi by 5 towards left, I'll get V1, isn't it? So how you'll be getting this? So how you'll be getting in the sense, so this point will be your pi by minus pi by 5. Okay. So this is your pi, this is your 2 pi, this is your 3 pi, and this is your 4 pi, right? So if this will start on here, so where this will be ending? So it will be ending here, right? And similarly, 1 second. Yeah. So the positive cycle will be like this, negative cycle will be like this. Again, the positive cycle will be like this, and negative cycle will be like this. Yes or no? So this width is basically again your pi, right? This width is basically your pi. So how much this will be then? What is the coordinate of this? So this is anyway, we know this is pi, this is 2 pi, this is your 3 pi, and this is your 4 pi. So this point, if I ask you, so this is your pi minus pi by 5. Okay. Similarly, this point, if I ask you, what is this point? So this point is your 2 pi minus pi by 5. If I ask you, what is this point? So this point is 3 pi minus pi by 5. I mean, with respect to 3 pi, 2 pi, so these all points are pi by 5 forward, right? And if I ask you, what is this point? So this point is 4 pi minus pi by 5. So now, so this is what waveform. This is nothing but your V1 waveform. Now, what is my need? My need is to plot this V3. Now, to plot this V3, what I'll be doing is, again, I'm drawing this. So I'll be taking this as the reference. Okay. So this is minus pi by 5. This is this, again this, again this, and again this. That means between this segment, so this is logic 1, and this segment, this is 0. And again, between these segments, so this is 1. This is 0. Okay. Why? Because to get this V3, again, I have to compare V1 with 0. So when V1 is positive, that means in this particular interval, when V1 is positive, I'll be getting the V3 is 1. Again, when V1 is negative, I'll be getting it is 0. So like that, I have plotted it. So if I ask you to, write the corresponding coordinate, so this is your minus pi by 5. So this is your pi minus pi by 5. This point is your 2 pi minus pi by 5. And this point is your 3 pi minus pi by 5. And the last point is your 4 pi minus pi by 5. 4 pi minus pi by 5. Okay, so let me do one thing. So I don't have any business to do with this. So I'm removing this. I don't have any business to, okay, 1 second. So let me highlight this point as well. It will be easier for me to handle then, right? 1 second. So this point is your pi. This point is your 2 pi. This is anyway 0. So where is 3 pi? So this point is your 3 pi. And this point is your 4 pi. Similarly, in this waveform, if I ask you, so this is the point which is pi minus pi by 5. And this point is 2 pi minus pi by 5. It needs patience. Okay. Similarly, where is this point? So this point is your 3 pi minus pi by 5. Similarly, this point is your 4 pi minus pi by 5. Okay. So I don't have anything to do with this as well now. So I can remove it. Okay. Okay. So now we got this one, and we got this one. So we have to basically do the XNOR of this to get V5. I mean XOR, not XNOR. XOR, right? It's XOR gate. So to get these outputs, so I'm calling this as V5. So this is my V5 piece. Okay. Now what is the property of this XOR gate? Property of XOR gate is when both inputs are different, output is 1. When both inputs are same, output is 0. So let us take these, my observations I'm taking from minus pi by 5 till this 4 pi. Okay, this is my observations. So between minus pi by 5 to 0, so you can see this is 0 and this is 1. So we'll get here 1. So this is your 1. Then between 0 to pi minus pi by 5. So this is the point which is pi minus pi by 5. Between 0 to pi minus pi by 5. So this is 1 and this is also 1. And 1 XOR 1 is basically 0. So we'll get here 0. Then between pi minus pi by 5 till pi. Okay, what is happening? So this is 1 and this is 0. So 1 XOR 0 is basically 1. So we'll get this. Then between pi to this point, which is your 2 pi minus pi by 5. Between pi to this point. So this is 0 and this is also 0. I mean, this segment I'm speaking about. 0 XOR 0 is 0. Then between 2 pi minus pi by 5 to 2 pi. So this is the point 2 pi. So you can see, I mean, I'm speaking regarding this gap. Okay. So this is 0 and this is 1. So we again getting this is 1. Again, between 2 pi minus pi by 5. Okay, till this point. I mean, till 3 pi minus pi by 5. So you can see it is again 1 XOR 1 is 0. This point is your 3 pi minus pi by 5. Again, between this point, 3 pi minus pi by 5 to 3. Okay. So this is 1 and this is 0. So this gap I'm speaking about. This is 1 and this is 0. So 1 XOR 0 is, again, it is 1. So this will continue like this till 3 pi. And so on and so forth. So what is this waveform? This waveform is V5. Okay. So now this, and what is this voltage? The voltage is 5 volts. Here you can see. So the output of XOR gates are 0 volts and 5 volts, right? So low logic is 0 volts and high logic is 5 volts. Logic 1 and logic 1 is equivalent to 5 volts. So this is what is nothing but my V5, and this is passed through a low pass filter, and I'm supposed to get the output of this low pass filter. What is the the next step we should be doing in this case? Yes, who are online, please respond in the comment. Nikhil, Mona Lisa, Sibani, you all people, please respond me. Now what's going to happen? If this is the square waveform, we are giving the input to the low pass filter, then what's going to happen? Yes, output of a duty cycle. Then we have to apply Fourier Series. Yes. Only DC component. How do you decide only DC will be passed? How to decide only DC will be passed? So basically, V5 is a periodic waveform. And if I ask you what is the period of this? So what is the period of this? So this is what is the period. So basically, this is 2 pi minus pi by 5 minus pi plus pi by 5, right? I mean this gap. So your this and this cancel. So the T naught is basically coming as pi. So T naught is coming basically is pi. So what is your 1 by T naught? So 1 by T naught is basically 1 by pi. And how much is 1 by pi is coming? How much is 1 by pi? 1 by 3.141. How much will it come? What is 1 by pi? What is 1 by pi? I want to know what is the fundamental frequency of this V5. So for V5, what is the fundamental frequency? What is the fundamental frequency? Fundamental is 955 Hz. No. How it is 955 Hz? How it is? What is 1 by pi? What is 1 by pi? 1 by 3.141. How much will it come? 1 second. 1 by 3.141. So this is coming 0.318. This is coming 0.318. So F naught is 0.31 of 8. So this is the fundamental frequency of this particular square waveform. So now if this is a periodic waveform and if you try to get this frequency contained, okay, so leave it the harmonics and whatever it might be. So we can say, like if this particular V5 waveform is containing fundamental first harmonic, second harmonic, third harmonic, etc. Okay, so then what's going to happen? Because the low pass filter cutoff frequency given 0.1 hertz. .318, na? Yes. 0.318 is the frequency you're getting, okay? And low pass filter, so this is basically 0. How much? 1 hertz. So this is your F. So this is your 0.1 hertz. So the fundamental component of this itself is coming in the stop band of this low pass filter, right? So if you're writing its corresponding Fourier series, okay, so what's going to happen? Only DC will pass. Because the Fourier series, if you want to write for this B5, so this is your A5 in A0, the summation n equals to 1 to infinite, an cos of n omega naught t plus bn sine of n omega naught t, right? So these all particular term, so this and this particular term, so they will have frequency more than the cutoff frequency of this, so only DC will pass, okay? And if only DC will pass, you have to find the DC of this. You have to find the DC of this. And how to find the DC of a signal? What is V naught of DC? That is the area divided by the time period. So time period we got, this is pi. And what is the area? Area over one time period is basically height is pi and width is how much? Pi by 5. So 5 cancel. So we are getting pi by pi. The answer is basically 1 volts. The answer is basically 1 volts. So depending on the cutoff frequency of low pass filters, the filter will allow only the DC to pass. It will block all the harmonics. Why? Because if I'm finding the harmonic, let it be first, second, third, fourth. By observing the symmetry, you can see which harmonics will present, which harmonics not present. But anyway, so even the first harmonic will not pass because the fundamental frequency of the signal is going 0.318. So if the first harmonic itself not passing, there is no question to think of second, third, fourth, and all. So only DC will be passed. So the answer is basically 1 volts. Okay. So what would have happened if I would have said the frequency is 0.4? Then what would have happened? So instead of 0.1 hertz, if I would have said this is 0.4 hertz, then what would have happened? What will the analysis might have changed if I would have set the frequency 0.4? If I change the frequency to 0.4 instead of 0.1, now this question will no more be a what? Objective questions. So this will be basically a subjective question then. Why? Because you have to find its corresponding Fourier series expansion and you have to find the fundamental term and accordingly you might have done it. Okay. But anyway, one thing I can tell. So because if I ask you to find RMS value, then you should be very careful. But if I ask you to find the average value, even if I give the frequency 0.4 hertz or 0.8 hertz, whatever it might be, you'll be getting the what? You'll be getting different sinusoids. And if you find the average value of the sinusoids, so definitely you'll be getting it is 0. So always you'll get the DC. So what is the average value? If I ask you, it will be always DC, right? But RMS value means you should be careful. Some people have doubts. What is this axis? Okay, some people have doubt. The axis which I have taken is omega t axis. Actually, it really doesn't matter. For example, you can think of like I have taken the axis omega t and you can think of omega t equal to theta. So basically with respect to theta, we have plotted. Now, some people might have doubts. Sir, here the frequency is 3000. Now, what about this 3000? It really doesn't matter. Why it will not matches? You see here. So you take any particular square wave, okay? You see any particular square wave form. Okay. So suppose this is the square waveform we are taking. Okay. So this is the square waveform we are taking. So this height is A, this is 0, this is t by 2, and this is t. So this is your x of t. So if I ask you what is the average value of this, your answer is A into t by 2 divided by t. So this is what is the x average. Now what I'm doing is, so now I'm giving you another signal where I'm saying, you tell me the average of x of 2t. Now if I ask you to find the average of x of 2t, so first draw the signal x of 2t. X of 2t, if I ask you to draw, So with respect to this, what's going to happen? So this is 0. So this is t by 4, and the period which was t, so that will be t by 2. I mean, if I take this is x of t, this is what x of 2 will look like. Now, if I ask you to find the average of this signal, so it will be again your area. I mean, this height is a, and the width is now it is t by 4, and this total time period which was earlier t, now this is becoming t by 2, right? So how much is it? Don't you think this and this are equivalent? So if you are simplifying this, you are getting this is a by 2, and how much you'll be getting here? So if you multiply 4, so you get 80, and this is 2t. So you can see here again it is a by 2 only. That means what? The average value of x of t and the average value of x of 2t, or if you take any scaling factor, it will be same. It will be same. Why I'm explaining this? So suppose the frequency is 1 instead of 3000 t, if this could have been 1, okay, and now it is 2, and now at later moment time this is 3000. So this scaling will not really matters. It will not matter, because if you are scaling a signal, its average value is definitely not going to change. Why would it change? It won't change. Sir, it will matter when we calculate the fundamental frequency. We are not taking our average. Yes. So if the question is to find, average value, it really doesn't matter. But if you have to get RMS value or exact amplitudes, it will definitely matters. Okay. So is it clear now? So I have taken, this is the axis, I have taken theta, but theta is equals to omega t. Fundamental frequency calculator seems to be wrong. How? How is it wrong? How is it wrong? Fundamental frequency of what? Fundamental frequency of this V5 I calculated. Fundamental frequency of V5 I calculated, and this is fine only, right? What was the period of that we got? The period of the V5 we got, it is pi. If the period is pi, so what is the frequency? It will be 1 by pi only, na? 1 by pi is coming 0.318. That is fine. Sir, but for frequency, we have to convert the axis in time axis, na? That is what I am trying to explain, Mona Lisa, in this case. Okay. As far as this question is concerned, it really doesn't matter. Why? Because if the DC is the concern, okay, so scaling is really have no impact. XOR gate output, yeah. You try it later. You take this, okay, fine. You can think of like how to plot this waveform. Okay, actually, if I ask you to plot this waveform, how it will be? How this will be? So you can think of this way. So suppose if I ask you to plot x of t is equals to sine of 3000t plus pi by 5, right? So you may do this way. So first you may plot x of t plus pi by 5. So this signal you scale it by 3000. So x of t plus 5 I have already shown you, right? So then you have to scale this t by 3000. I mean the scaling factor was 3. So yes, I have taken that axis as omega t. Yes, I have taken that axis omega t. So that's what I'm saying. So this is your t plus pi by 5, right? So then you have to scale it by 3000, and you again carry out the process and let me know if they are getting any changes. You'll not get any change. In other words, I'm saying if this signal is sine 3000 t plus pi by 5, or this signal is sine of t plus pi by 5, in both cases, the answer will be same. That's what I'm saying. Okay, come to this problem. This question's okay. 2 square waves of equal period t, but with a time delay tau, are applied to a digital circuit whose truth table is shown in the following figure. Okay, the high and the low levels of output of digital circuits are 5 volts and 0 volts respectively. Which one of the following figures show the correct variation of the average value of output voltage as a function of tau, where tau is varying between 0 to t by 2? Okay, so let's come to this question. So if you see this particular truth table, this truth table is the truth table of a XNOR gate, right? So because when inputs are same, 0, 0 for 1, 1, we are getting it is 1, and when inputs are different, we are getting this 0. Okay, so it's a XNOR gate. So you have two inputs, namely X and Y. So they are XNOR. And we have to give the variation of what? This average value of output of this XNOR gate. So what we can do is, so I'm taking an axis. So here this is 0. So this is the time axis. Then I'm taking a point tau. Then I'm taking a point t by 2. Then I'm taking a point tau plus t by 2. Then I'm taking a point t. Okay, like this. So between 0 to tau, so this is what tau is. This is 1 and this is 0. 1 XNOR 0 is 0. Between tau to t by 2, okay, between tau to t by 2. So I mean, this is your 1 and t by 2 will come somewhere here. So this segment. So 1 and 1. So if they're XNOR, so you'll get it is 1. So you'll get it is 1. Then between t by 2 to tau plus t by 2. So this is what tau plus t by 2 is. So this segment, which is 0, and this is 1. So 0 XNOR 0 will be 0 only, right? Then again from tau plus t by 2 to t. So this is your tau plus t by 2 and this is your t. So this is your t. So both are 0. So 0 XNOR 0 is basically 1. So up to t, you'll get it is 1. And beyond t, okay, so this is 1 and this is 0, it will be 0. And so on and so forth. So this is what is the waveform of X XNOR Y. X XNOR Y. And this amplitude is basically 5 volts because it's given 5 volts and 0 volts. So this is 5 volts and logic low is 0 volts. Okay. So this is the waveform. And if I ask you to find the average value of this, average value is again the total area of area divided by the time period. Okay. So this is, if I say X XNOR Y is equals to Z, so your Z average is equals to area over one period. Okay. So area, so this is 5 into what the width of this? This is tau minus t by 2 divided by the time period. What is the time period if I ask you? So time period is basically t by 2. Isn't it? Time period is t by 2. I mean, this gap, if I ask you to find it out, so this is coming t by tau plus t by 2 minus tau. It is t by 2. Height is 5 and width is tau minus t by 2. So you multiply 2 by t. So it is 10 by t into tau minus t by 2. Okay. So if you multiply 2 by t, so 10 by t into tau minus t by 2, this is 1, right? So this is what is the expression of Z average you are getting, right? So you may plot it by taking some values. So how do you plot it? So to plot this, okay, so I'm taking this axis. This is the tau axis. This is 0. So we are supposed to give this with respect to tau. You see all the options. So with respect to tau, we are asking. So if tau equal to 0, in this, if I substitute tau equal to 0, so what's going to happen then? If I substitute, it is 0. So you can see. So this waveform, if I substitute here tau equals to t by 2, so you'll get it is 0 only, right? So if you take some points and if you join it, t by 2 minus tau you are getting now. Okay, t by 2 minus tau. Yeah, it is t by 2 minus tau. Sorry, it is t by 2 minus tau. So this is t by 2 minus tau. Yes. So you take tau equal to 0 if you take. So in this, if you substitute tau equal to 0, so you are getting it is 5. You substitute tau equals to t by 2, you'll get it is 0, right? And if you take some other variations, and if you join them in freehand, this is what the waveform you get, and this is given in option C. Okay. Yes. Not this one. Let's solve one more question, this one. Okay. This question, let's try to solve. In the circuit shown below, the light dependent resistors LDR. Okay. So this is a light dependent resistor. So the resistance vary with respect to light. Receives light from LED. Okay. So this is receiving the light from this LED. The LDR has resistance 5 kilo ohm and 500 ohms under dark and illuminated condition. That means this particular device, okay, so this can have resistance 5 kilo ohms or this can have resistance 500 ohms. So when it will be 5 kilo ohms, 5 kilo ohms when it is dark. Dark in the sense when LED is not glowing, okay. So LED off. So the resistance of this device is 5 kilo ohms. And when LED is on, the resistance of this device is 500 ohms. Because you can see here dark and illuminated respectively. So the dark means 5 kilo ohms. The dark means what? When LED is not glowing. So when LED is not glowing, the resistance is 5 kilo ohm. When LED is glowing, the resistance is 500 ohms. Then it is given the LED is off at time t less than 0. So this LED is off for t less than 0. And at time t equal to 0, switch S1 is closed for 1 millisecond and then kept open thereafter, right? So this is a switch S1. So this is a switch S1. So it is said that this switch S1 is closed at t equal to 0 for 1 millisecond. Time t equal to switch S1 is closed for 1 millisecond and then kept thereafter. That means this switch was closed, okay, for 1 millisecond from t equal to 0 and then it is again open. That means at 0 it is closed and 1 it is open forever. Okay. Assuming 0 propagation delay in the devices, then which of the following option is true with respect to the LED? Option A, the LED turns on when S1 is closed and remains on after S1 is open. Option B, LED turns on when S1 is closed and turns off after S1 is open. Option C, LED turn on when S1 is closed and toggles periodically from on to off after S1 is open. And last option is telling LED remains off when S1 is closed and continue to remain off when S1 is open. So basically, depending on these switching actions, we are supposed to tell, okay, what the LED is. If the switch is closed, whether LED will glow or not, and the switch is open, whether LED will glow or not. So based on that, these 4 options are given. And if you see, it's actually SR flip-flop, okay? But the inputs are S bar and R bar, right? So if you want to make use of truth table of SR flip-flop, okay, you have to think with respect to SR, not with respect to S bar and R bar. Okay, so see what's going to happen. Any idea, please? It's a good thinking-based question. So one thing, let us see. Okay, if LED is on, okay, if LED is on, so the resistance is 500 ohm, right? So if I say this voltage is Vx, then what is Vx? So Vx is 1000 divided by 500 plus 1000 into 5 volts. If this is the Vx, so the Vx is, I mean, this is the voltage. So by voltage division rule, so this is 1000 divided by this resistance is now 500. So 500 plus 1000 into 5. Okay. Similarly, if LED is off, then your Vx will be how much? 1000 divided by 5 kilo ohm is given, right? So 5000 plus 1000 into 5. So how much is coming? Let me know. Because depending on Vx, so if I denote this by V naught, so this V naught will vary depending on Vx because this is fixed to 2 volts, right? So whether V naught is 1 or 0, that depends on Vx. That means when LED is on, what is this V naught? When LED is off, what is this V naught? So this is coming 3.33 volts. And this is 5,000 divided by 6,000. So this is basically 5 by 6. So what is 5 by 6? Is 0.83 volts. So, yes. Okay. So when LED is on, so this voltage you are getting it is 3.33, and when LED is off, this voltage you are getting is 0.83, right? So when LED is on, what is V0? So if LED is on, what is V0? If LED is off, what is V0? So if LED is off, so this voltage is 0.83. So here 2 volt is greater than 0.83. So V0 is equals to logic 1. And when LED is on, okay, when LED is on, so V0 is equals to, so Vx is equals to 3.33. So 2 is less than 3.33. Here it is 0. Here it is 0. Yes. Okay. I mean logic 1. Logic 1 means 5 volts. 0 means logic 0, that is 0 volts. Okay. Now what is the consequence of this? So so if I want to summarize this, I can think this way. Okay. If LED is on, your V0 is equals to how much? 0. If LED is off, your V0 is equals to 1. But what is the consequence on S and R? So if you see this, okay. So if you see this, V0 is equals to 0. So what is happening to S and R? And what is happening to S and R in this case? What is S value? What is R value? R bar is high, so that means R is 0. So R is 0 in both cases because this is fixed to high. R bar is high, that means R is 0. So what is the, so this V0 is connected to S bar only, right? So V0 is equals to S bar. So V0 is 0 means S is V0 bar, right? So S is 1. And in this case, when V0 is 1, I mean S bar is 1, that means S is basically 0. So this is the consequence. Okay, that means when V0 is 0 or when LED is on, so you are getting SR input to SR flip-flop is 1, 0. Note that these are S bar, R bar, I'm writing with respect to SR because I want to make use of truth table of SR flip-flop, not S bar, R bar. We are not comfortable to handle S bar, R bar, we are comfortable to handle SR. So I'm writing in terms of SR. Okay. So now the, okay, this the situation is, okay. So this is what the conclusion is. If LED is on, SR flip-flop is receiving 1, 0 input. If LED is off, SR flip-flop is receiving 0, 0 input. Okay. So if 1, 0 is the, you know, this thing. So if you remember in SR flip-flop, so we get Q plus equals to 1. And if 0, 0 means we get Q plus equals to Q. This is what the standard thing in SR flip-flop, if you remember. Now you see, so this is what is the overall conclusion of the story. Now let's come to the question. The question is, so if the switch is closed, what is going to happen? So first thing is, if the switch is closed. But switch is closed for, okay, switch is closed for what time? So from 0 to how much? 1 millisecond, right? This is what is given, switch is closed. Now you think yourself, when the switch is closed, now what is the situation of LED? And when the LED glows light when it is in forward bias. When the switch is closed, now P side is connected to 5 volt through the 220 ohm resistor and N side is connected to ground, right? So when switch is closed, so I can think of this is my LED is, and this LED, the negative side, the switch is closed, is connected to ground. I mean, ground means we are connecting 0 volt to this. So we are connecting 0 volt to this when the switch is closed, right? And P side, we are connecting it to a resistor of 220 ohm, and this is 5 volts. Okay. So whether LED is forward bias or reverse bias in this case, of course it is forward bias. If this is the LED, P side we are connecting to 5 volts through 220 and N side is 0 volts. So definitely it is on. So switch is closed means LED is on. Switch is closed means LED is on. So option D is gone. Remain off when S1 is closed. That's not going to happen. Okay. So answer could be any one of this ABC because you can see turns on when switch S1 is closed. Okay. So S1 is closed. So this is the situation. Now we have to see what's going to happen if S1 is open. See, If S1 is closed, so LED is on, that is fine. But what is the consequence of this? So LED on means I have to refer this particular statement. So if LED is on means S is 1 and R is 0. So that means your Q, so this is basically 1. 1 means basically it is 5 volts. Logic 1 means in terms of voltage it is 5 volts. And this is of course complement to this. So this is basically 0 volts. So when LED is on, I mean when the switch was closed in this interval 0 to 1 millisecond, so Q was 5 volts and QR is 0. So this 5 volt is connected to this particular, what I can say to this particular NPN BJT. So this is the story now. Okay. So now the moment when switch is open, okay. Now when the switch is open, now what is happening? When switch is open. So when the switch is open for what? For t greater than 1 millisecond. That is what is given. It is open at 1 millisecond and thereafter it is open only. So for t greater than 1 millisecond, it is open. Now what is the consequence of this? When switch is getting open, okay. So now we have to see what is happening to the LED. So again, LED, if I see, so the P side, we don't have anything changed. So this is again 5 volt, this is again 220 ohm, and this is the LED, right? But what is connected to N side, that depends. Earlier case, when the switch was closed, it was connected to ground. But now what it will be? So it all depends on the situation of this BJT. If BJT is, let's say, on, so ideal case means it will be again connected to 0 volts. If BJT is on. If BJT is off, so this will be basically open circuits. Open circuit means it will be definitely in the off state. LED will be definitely reverse bias. Are you getting or not? So if the switch is open, what is the situation of N side? You have to see whether N side will be connected to 0 volts provided transistor is on, or if the transistor is off, it is open circuit itself, it is off. So that means the N side is kind of open circuit. So of course LED will be off. So now we have to see basically when we are connecting or when we are removing the switch, when we are opening the switch, now what is happening to this particular, like BJT? That is what the situation is. Let us assume, okay. So what is going to happen to this BJT means, let us assume that the LED is off. Let's assume LED is off, and we'll again cross check whether our assumption is correct or not. In diode, you might have seen this, the technique you might have done many times. Like what we used to do in that case. So we assume something and we cross check our assumption, right? So in this case, let me assume the, LED is off. So when I say LED is off, now the situation is S equal to 0 and R equal to 0. So this is the situation. If I assume the LED is off, if I assume LED is off, that means when LED is off, this LDR resistance will be what? This will be 5 kilo ohms, and consequently we'll get this input SR, that is basically 0, 0. So if I think of this is 0, 0, okay. So Q plus equals to Q. Okay, what is Q? What is the previous state? The previous state was 5 only, right? Previous state was 5 only. So that means Q plus equals to, again, it is 5 only. The same 5 volt you'll get here only. Okay. And when this is 5 volt, don't you think this BJT will be on? This BJT will be on, na? So this BJT will be on means what is happening then? This LED will be definitely what? On means LED will be in on state only. Once again, I'm telling you, listen carefully. So if I assume that when the switch is open, LED is off. This is what I have assumed. Now I am cross-checking my assumption. Okay. So I have assumed LED is off. So as a consequence, so if LED is off means we got S equal to 0, R equal to 0. So S equal to 0, R equal to 0 means Q plus equals to Q. So Q plus equal to Q means what was the earlier state of this Q? This was 5 volt only. So if I assume the LED is off, so I'm getting it is again 5 volts only. And if this is 5 volts, this transistor is coming what? This transistor is on only, na? This transistor is on because this is anyway connected to ground. So if you're connecting 5 volt to this base, so this will be again on only. And if the transistor is on, so there is no question that this LED will be off state. If transistor on is happening, so it means compulsorily LED cannot be off state. So my assumption was wrong. That means LED is on. So what is the answer? So first page was correct. Turns on when S1 is closed. This is fine. Remains on after S1 is open. This is correct. Remains on after S1 is open. Because if I'm opening S1, I have assumed that LED is off, but I'm checking that my assumption is wrong because LED is coming on. If I assume LED is off, so the transistor is coming on. And if transistor is on, LED cannot be off. So of course, answer is option A. Option B, turns on when S1 is closed. Turns off after S1 is open. So this is what we have assumed. It is not happening. So option B is wrong. Option C is saying toggles periodically from on to off after S1 is open. No. So because there is a chance of toggling provided if this Q is fluctuating between 0 and 0 and 0 and kind of things. So that situation is not happening. So there is no chance of fluctuations. So the answer is definitely A only. How many of you understood this one? How many of you understood this question? So such kind of questions sometime you'll get, okay? And these are very few questions in the GATE exams, and very few students only can answer such kind of question, right? So it needs thinking skill. Have you understood this? Yes or no? Have you understood? Can I get your comments? This question, all of you can solve, so I'm not solving this. Okay. So this is left, so you can try this. You can take a screenshot of this. You can try this. Okay, Nikhil understood. Monalisa also understood. Good. Okay, you can take a screenshot of this and you can solve this problem. Okay. It's a very straightforward flip-flop based question. I mean, counter-based question. Okay. Okay, Sivani also fine. And what about this? What about this? If you understood that low pass filter problem, so this question also you should be able to answer. And this question is asked in Civil Service Examination 2005. So hopefully in the next class, I'll be taking this. A sequencer circuit has one input and one output. The state diagram is shown in the figure. Design the sequence circuit in detail. I would say Civil Service exam questions in electrical engineering. Civil service has optional electrical engineering. In electrical engineering, digital is in the course. I mean, digital is in the syllabus. And from that, this conventional question was asked. So this will take in the next class. Okay. So this question is really good questions, right? It needs good amount of thinking skill to answer this. Okay. So that's all. So this is what for today. Okay. So I'm stopping the session here. In the next class, we'll again come up with some more interesting questions. Thank you for attending the class.